Alright, this is problem 4.22 for our legacy project. We have a cylinder of very long length, and it's wanting us to find the resulting electric field if you fill the inside with the inside of a cylinder with the dielectric and you place it in an electric field. I chose the electric field facing the X direction. Sort of looks like this. The radius of the cylinder is A, and the potential function, which is derived in a previous problem. I'm not going to redo that. So, very little complex. This is the potential function inside and outside of the cylinder. It is derived in a previous problem. I'm going to use it. Here, I like to set out the boundary conditions that we're going to be applying to this particular problem. So let's do that. So the boundary conditions, we've got the potential function inside is equal to the potential function outside at S equals A. So that's saying the potential on the outside, the potential at all points on the outside of the I guess this surface, I guess you could say, is equal to the inside. It's just a continuity. Alright, next. The electric field, or this is I'll go ahead and take a second here. This is the permittivity on the inside, or the permittivity times the differential of the inside with respect to S is equal to the permittivity of free space, the outside, dV, or I guess it's a partial, so, and ds. And is, see if I can still see that on there, equals A. This is going to take some time, I can already tell. Alright. Third condition, and these all you can figure out. I don't really quite understand this one. I actually used the example that's in the book for, let's see, what example is that? Example 4.7 in the 4th edition of Griffiths. And V out is negative S cosine phi for S much greater than A. So the potential on the outside approaches this function for S much greater than A, basically at infinity or whatever. Okay, so we have our boundary conditions, and we want to look at what happens inside the cylinder. Inside the cylinder, S can be equal to 0. So the potential function can be reduced because at S is equal to 0, we have here 1 over S, and that is undefined there. It'll be infinity. So we can, inside the cylinder, that potential function blows up here, and then all we're left with is this. So we can write two equations for the inside and outside from this one equation. Inside, the potential function of the cylinder will blow up at 0, and at infinity it'll blow up here, S to the n. So those two need to be considered. Alright, so let's look at the potential function inside the cylinder. Once again, because at s equals 0, this term blows up. So we're only left with the other terms. Here we go. And the potential function on the outside. Okay, inside the sphere, we're only left with this term here. And on the outside, I used equation 4.45 in example 4.7, and which has to do with one of the boundary conditions. And it says that the potential on the outside is equal to E naught sub r cosine theta plus, and then your potential function. Don't honestly understand why, but it does. So, and we're left with on the outside the s to the negative n, a sub n cosine n phi plus b sub n times the sine of n phi. Wonderful. Moving forward, condition 1 states that the outside is equal to the inside at s equals a. So let's apply that. Alright, so here are two equations equated to each other, and if we let n phi be equal to a, basically let this angle measurement be aligned with the y-axis, which can be, you know, pi over 2 or 3 pi over 2, then it allows us to solve for a couple of coefficients. So let's do that. Let's say these are equal to pi over 2, for example. So cosine of pi over 2 is 1, sine of pi over 2 is 0, and then we have a 0 over here. It basically simplifies this down to what we have here. So the cosine term went to 0, sine term went to 1, so we have just the coefficients left. The boundary condition went to 0, and we're left with this. And from this, we can basically conclude that b sub n is equal to d sub n, which is equal to 0 for all n. That, I believe, is also in the it is also in the example. Yes, it is. Same kind of trick. Alright. So, let's continue. And so we've determined two of the coefficients are equal to 0. That simplifies our problem a lot. So now it looks like we're going to be using condition number 2. Epsilon summation. Actually, I'm going to go ahead and I'm going to just write this all out and go from there. Okay, so using that boundary condition, we're left with this. And if we divide this epsilon naught out over here, we have epsilon naught, basically the relative permittivity is equal to this. And we put that back into the equation, and doing the same thing as before for all n. If s vectors align with the y-axis, those terms drop out with the cosines, and we're left with this. And except for a special case where n is equal to 1. Whenever n is equal to 1, we're about to see what happens then. But so basically our function is 0 everywhere except for when n is equal to 1. So let's take a look at that special case. Okay, so if n is equal to 1, we are left with basically cosine phi and all these terms here. So it basically will simplify to, for n is equal to 1, follow me here, it basically simplifies to that, and you should be able to work that out pretty quick. So here we go. We have a to the 1, c to the 1. These terms just go away. This goes away, and those go away. And that is because we ended up dividing across the board by cosine. It's a like term, so just they can all go away. And let's continue here. Okay, so we're left with this, and if you basically, that drops down to this once you get rid of those cosines. And from here we use condition number 2. Let's go back to that. That says the basically that the derivatives have to be equal to each other at s is equal to a. So let's do that. Alright. So for as n is equal to 1, we're left with basically this after those cosines go away. And then if we use condition number 2, it says the derivatives and the permittivity coefficients, basically if you take the derivative of that, you basically end up getting into the -1, and if n is equal to 1, you get a to the 0, c1 minus e0, and a to the -2. And basically if you take both of these two equations and solve for a1, well, set them both equal to a1, and then solve for c1, you get this. I will show you my, just to save some time on this video, here's what the algebra should look like for that. So you can see here you get down to the relative permittivity is actually equal to 1 plus x sub e, which is, and then that can further simplify down to -2 e0 over 2 plus x sub e, which is what we have here. So we have determined that the coefficients c and a are 0 for all n except for n equals 1. The coefficients b and d are 0 for all n. So we can look at our potential function from earlier, and we can go ahead and say the d, and it's the question was asking for the potential function on the inside of the cylinder, so we're not concerned with the outside at all. Alright, so and see, well, basically after equating all of our coefficients, we're left with the potential function equal to this, and essentially if we take the we take the derivative of the potential function, we get the electric field. And from the book, didn't quite understand this as well, but this r cosine, basically you take the derivative of this, they said this is equal to x, and then you're basically just left with this in a direction. So that's essentially what I did here, and this is the resultant. So that's it, and that should actually be in a direction. The direction is in the x direction. But that's what that is. This is supposed to be the x hat direction, I believe. X hat direction. That's it. That's all I got. Never done this before. Did not enjoy it at all. And I'm glad I'm not going to be a professor. That's all. Thank you.